let's start with the topic which we need to discuss. In the very last class, we have just finished with our topics, that was black body radiation. I also told you that we need to discuss basically two concepts. First one is the due nature of our matter. It could be either of light, that is particle nature, and the wave nature. Wave nature we have discussed very well. And the particle nature we are going to discuss, in which we have discussed our first topic, that was black body radiation. And now we're left with only our second topic, that is photoelectric effect. After that, I also told you that we will discuss the topic that is atomic spectra. And then we will jump to the topic that is our Bohr's atomic model, which is your main topic, that why do we need to study Bohr's atomic model and what are its limitations. After that, we will move to electronic configuration, which is the most important topic of this whole chapter. Okay, so let's start with our today's topic, that is photoelectric effect. Let's start. See, class, I have already told you that in photoelectric effect, there is no effect on the wave nature. We have to discuss here the particle nature of our light. The photoelectric effect was discovered by a scientist, and he told that whenever we can say radiate a light, we fall a light on a metal surface, and this metal surface could be either cesium, potassium, rubidium, or sodium, or we can say platinum, iridium, any kind of metal. Whenever a light strikes on the surface of metal, I have told you that there is some points of electrons, there is some energy that is going to be released soon and soon. And that was the point, that why do we need to discuss our photoelectric effect. Okay, I'm again repeating, listen very carefully. Whenever a ray of light strikes on the topic, on the metal, and after that, whenever it strikes, some electrons are going to be released in the form of packets of light. And that's why here we are going to study the particle nature of light and the photoelectric effect. Okay, so the scientist did nothing. He just set up the whole experimental setup, in which he put a vacuum chamber, as the electromagnetic radiation do not require any medium to travel. In the last class, I have told this very carefully, very detailed, that in our vacuum chamber, our electromagnetic radiations can travel very easily, as they do not require any kind of medium. Okay, so first of all, he set up a vacuum chamber, and he put an ammeter just to check out the electric current, and a battery with the positive, negative, the whole terminal. Okay, I think you know very well about the battery. It's made up of more than 2 cells, and the cell is of positive, negative, so it's a battery. Okay, so a battery, an ammeter, a detector just to check out, just to detect whether the electrons are emitting or not. So what did he do? He strike a light on the metal of surface, and the electrons are coming out. These electrons are coming out. These electrons are ejected whenever the light just strikes on the surface of our metal. Okay, so he gave us 3 different observations. The first observation, according to him, as soon as the light strikes on the metal, the electrons are ejected without any time lag. That means it's no possibility over there that I'm striking my light, and after 5 minutes, 10 minutes, my electrons think that yes, we should go out, we should eject out. There is nothing like that. According to him, whenever the light strikes, as soon our electrons are ejecting out. Okay, so according to him, it was the first observation, the light strike, electrons are coming out. Secondly, he said the amount of electrons which are emitting out from the metal it depends only upon the intensity of light. How strong light, how bright light we are using, on this intensity, our amount of electrons are ejecting out. That's quite a normal thing. I think I don't should explain more about this line, that whenever the intensity is high, the amount of electrons is high. Okay, and third point he gave in a numerical way, in a mathematical calculation, that there should be a minimum frequency which is known as threshold frequency. In the very last class, I have told you that our frequency is denoted by nu. Okay, so according to him, there should be a minimum frequency known as threshold frequency denoted by nu naught. This is not O, this is nu naught. Okay, 0, you can say this is nu naught. Okay, so according to him, there should be a minimum frequency with which electrons are ejecting. This is known as nu naught, or we can say threshold frequency. Threshold frequency. This is just another name, just another denotion. So don't worry about the definition. Not about the definition, sorry. Not about the meaning of threshold frequency. It wants to define us that it is that minimum frequency at which our electrons are ejecting out. Okay, so he said us that our energy E equals to h nu, where h is Planck's constant and nu is our frequency. This was given by him, and he also said that after an electron has acquired this threshold frequency, only then his kinetic energy, the kinetic energy of electron, is at that level that it can eject out. I'm again repeating, listen it very carefully. According to the scientist, he said that first of all, any electron must require a particular frequency known as threshold frequency nu naught. When an electron has acquired that frequency, after that, electron has acquired the kinetic energy, and kinetic energy is the only energy which is used for the motion of any kind of moving thing. That's kinetic energy. That's the definition of kinetic energy. So electron pick up that kinetic energy and then they just eject out from the matter. Okay, so he just merged out all three concepts and gave us a numerical formula, that is h nu equals to h nu naught plus half of mv square. I think we know about the concept half mv square. What is this? This is kinetic energy. You have heard about this in your physics class since 9th class. Kinetic energy equals to half mv square. Okay, so he told us h nu equals to h nu plus half mv square. That is, energy is equals to the kinetic energy of electron plus threshold frequency, because that is the only minimum requirement to eject an electron. These all three concepts was cleared by the photoelectric effect. Okay, I hope I have made sense to this topic. And if you have any kind of doubt, let me know. We will discuss after the class. Okay. So let me again just brief recapitulate the whole topic. In the photoelectric effect, we have a vacuum chamber, and according to the scientist, whenever a ray of light strikes on the metal, the electrons start ejecting out from the metal with the threshold frequency nu naught, so that the kinetic energy so that electron pick up the kinetic energy and can be easily ejected out. That's the first point. Second point, intensity of light must be directly proportional to amount of electron. That is, if we are using light with strong intensity, with strong energy, the electrons would be easily ejected out. Okay, and the last one, he combined up the all things and said h nu equals to h nu naught plus half mv square. This was all about photoelectric effect, and we have some numericals on it which are important. On these two numericals, I hope you have got the photoelectric effect. Okay, so let's move to our topic, next one, that is the numericals. Okay, let's move with the top with the numerical that's known as calculate energy of 1 mole of photons of radiation whose frequency is 5 into 10 raised to power 14 hertz. Okay, class, uh, I think I didn't tell you about the photons, what actually photons wants to explain you. Photons means whenever light strikes, the electrons are ejecting out. And I have told you that these electrons, whenever released, they release the energy in the form of packets of light, known as quantums or photons. Okay. So whenever we got a question related to photons, that means we need to put this particular equation. That is E equals to h nu. Photons means we can say light. Photons is related to packets of light, or we can say source of light. Okay, so let's go with the numerical. Calculate the energy of 1 mole of photons of radiation. I'm going to run this. Okay, the numerical is we have to calculate the energy E, and the frequency is known as, which is given 5 into 10 raised to power 5 into 10 raised to power 14 hertz. 5 into 10 raised to power 14 hertz. Okay, we know very well our numerical formula, that is E equals to h nu. We have to calculate the energy. H is your Planck's constant, which we have discovered in our last lecture. H is Planck's constant. I have told you that you must remember its numerical value. That is 6.6 into 10 raised to power minus 34 joule per second. So 6.6 into 10 raised to power minus 34 into न्यू कितना दिया अभी हमारा 5 into 10 raised to power 14. So we would solve it. It would be around minus 20 joule, because this is joule per second and this is also per second. We cancel out. This is our hertz. So it would be the energy in the form of joule. We would solve it, whatever, I think it would be almost 30 point something. Okay, so this is our first numerical. And also, whenever we are talking in our chemistry, do one thing, put the decimal after 1 point. So it would be 3 point, suppose it's 30.2, it would be 3.02 into 10 raised to power minus 19. Okay, just to make our concept more clear, just to make it a little bit more beautiful into chemistry language. Okay, nothing else. It's also good, but it would be nice. Okay, and the numerical we have discussed. Last one, let's discuss the numerical based on the threshold frequency. Problem number 2.9 given in your NCERT book. The threshold frequency nu naught for a metal is 7 into 10 raised to power 14 per second. So the nu naught is given as 7 into 10 raised to power 14 per second, and the frequency of the radiation of metal, that is known as 1.0 into 10 raised to power 15 per second. Calculate the kinetic energy of electron. So we have to calculate the kinetic energy of electron, which is equals to half mv square. So what's the formula? H nu equals to h nu naught plus half mv square. Don't confuse, this is nu and this is v, that is velocity, or we can put it over here, the kinetic energy. H nu minus h nu naught equals to half mv square. H could be put as common, nu minus nu naught equals to kinetic energy. We have nu naught, we have h, just put over there and we will get the kinetic energy of our electron. So these are the simple numericals based on a very simple concept, that is photoelectric effect. The numericals are just The formula based, we have to do nothing, simple calculation if you know very well the formulas. Okay, so be careful with the formulas. And this was all about the photoelectric effect. The photoelectric effect and the black body radiations, both these proved are dual nature of light, that is the particle nature of light. Okay, this was all about the particle nature of light. And lastly, we are left with the topic atomic spectra. This is the last topic, and then we will move to our topic Bohr's atomic model. Okay, so let's start the last topic, that is known as atomic spectra. I hope you have got this photoelectric effect, the numericals too. So now let's move to our topic, what actually atomic spectra wants to define us. Atomic spectra. Okay. Before going to detail, you know very well about the spectra, which is also known as spectrum. In the last topic, what we have discussed that whenever these, remember we have discussed this one in Planck's radiation theory. We have discussed that these electromagnetic radiations, whenever release electrical and magnetical wave, after combining, they behave like a whole pattern, and this pattern is known as a spectrum. The same way we are going to discuss here atomic spectrum. What atomic spectrum wants to define us, what atomic spectrum is actually mean to us. Okay, so let's define. Let's start with very basic concept. See class, we know very well that this is the very basic law of universe. Nothing can be in the very high excited state for a long time. Okay, so what happens whenever we throw a light on any kind of atom, like we are taking hydrogen, we throw a light to hydrogen, the electron of hydrogen are right now in the ground state. Now what are ground state? See, this is our atomic model, this is our atomic structure, that our electrons can jump from one level to another level. This is the basic concept of atomic structure. And in atomic structure, the electrons have ground state. That means the energy is lowest over there. The electrons, the protons, the any kind of spherical things, they are at rest right now. So the ground state means they are at the rest, they are not moving. Okay. So suppose this is ground state and this is electron. This is the representation of electron, which you will discuss in the same chapter, but after 2-3 more lectures. Okay. This is the denotation of an electron. This is present in the ground state, and suppose this is your excited state. Now what is happening? Suppose I am throwing a light. This is a radiation of light on the electron. When an electron was present on the ground state, whenever an electron was present over there, and I just throw a radiation of light, suppose I'm taking an example of hydrogen atom. I just put up an hydrogen atom and I throw an radiation of light on that atom. What's happening? Our electrons were just resting out, they were just chilling out, and they were present in the ground state. First thing, what happened whenever I put the light on it? The electrons, after getting that particular energy which I provided with the help of light, they started to move to the excited state. Okay, that means whenever they get the energy, after absorbing that energy, they move to the higher state known as excited state. Okay, but I have already told you before the beginning that this is the law of nature. They cannot exist in the in the excited state with the energy for a longer time. They have to come back, they have to release that energy. So what's happened? Whenever they jump from the ground state to the excited state, After some time, they have to come back. So they have to release that particular energy. Whenever they release that particular energy and come back from excited state to the ground state, this energy releases in the form of radiations, and this radiation is known as emission spectrum. Emission means exit. Emission absorption means we are getting that energy absorbed out. Emission means we are emitting that energy, and this energy is emitting in the form of radiations, which is known as emission spectra, which is known as emission spectra. This was the whole basic concept of emission spectra. Rest is the numerical concept, which would I tell you, but this is the main concept. The ground state present over there, absorb the energy, go to the excited state, and after some time, when the energy is more over there, they come back and release the energy. The energy which is released out, this is in the form of spectrum, this is in the form of radiations, and this is known as emission spectrum. Same as it is, we have also absorption spectrum, but that is quite complex and that we would not discuss right now. That's higher beyond of your syllabus right now. Okay, so we have to just discuss the emission spectrum. Ground state, excited state, the energy is released out in the form of spectrum. Okay, so this is the basic concept. How much can we left with? Okay, so this was the atomic spectrum. Now, what's happening? I'm just taking a simple example of hydrogen. The concept is clear to you. Now the spectrum is released in the form of lines. Let's discuss how does these lines occur to us. Line spectrum of hydrogen. What I'm going to tell right now, this is super important for your exam point of view. A question from this topic would become definitely in your MCQ or in your 2 to 3 marks question. That is, whenever an hydrogen releases energy, it comes in the form of lines, which is known as line spectrum or emission spectrum. Okay, and whenever he releases lines, these lines have been discovered by so many scientists, and different line was given the name by different scientists. Okay, and you have to remember this. The first one is Lyman series. Second one is Balmer series. Then is the Bastian. Then is the Brackett. These all are the name of scientists. Okay, and the last one is P-Fund, and above all is the infinite. Okay, just give me 1 second. Okay, let's start. Suppose this is n equals to 1, that means ground state. This is Lyman series. This is Balmer series, n equals to 2. This is Bastian series, n equals to 3. N equals to 4, Brackett, n equals to 5, P-Fund. You have to remember up to the 5. Lyman, Balmer, Bastian, Brackett, P-Fund. Okay, and we have a simple concept to remember this, which is known as the line spectrum of hydrogen as the form of nu bar, which is equals to a constant 1 by n1 square minus 1 by n2 square, where n1 could be 1, 2, and so on, and n2 should be 2, 3, 4. These 2, 3, 4 is the higher, and n1 is 1, 2, 3. Okay, so if we have n1 equals to 1, that means we have Lyman series. If we have n1 equals to 2, that means Balmer series. Balmer series is only series which lie in the visible region. That means this is the only series that we can see through our eyes. Okay. Then if n1 equals to 3, this is partition, n1 equals to 4 bracket, n1 equals to 5 P1. Okay. This was whole the concept which is given by the line spectrum, known as also emission spectrum. Okay, ji? So this was the concept which I wanted to deliver you. Now let me just little bit explain how do we come to know about this topic when 09.677. This is nothing. This is just a Rydberg constant. We shouldn't remember much more about this. Okay. So guys, please keep remember this thing that N1, N1, 1, 2, 3, 4. On the basis of this, we have different type of series: Lyman, Balmer, Paschen, bracket, Refund. And the Balmer lie in the visible region. Now the question arises: how do we came to know that these lines have been arised out? I have already told you that they are coming back from the excited state to ground state, and they are releasing radiations. Whenever they are releasing radiation, they fall in different type of frequency region, because they are the radiation. They must have a particular amount of frequency. The radiation which are releasing out, that radiation fall in which region, that depends upon whether it is ultraviolet or it is visible or these are infrared. First one is, second one is visible, and these all are infrared. And I am stressing only on the Balmer because this is visible to us. Okay, so this is something which we can see whenever they release radiation. Okay, ji? So this was the whole concept about the line spectrum. So in today's topic, we have finished our wave nature, particle nature of light, that was all covered. And lastly, we have covered our atomic spectra, in which only we have to discuss the concept of hydrogen spectra, in which we have discussed this series diagram. This is very vast in details in the book also, but you have to keep remember these particular series. Okay, that is important. In the next class, we will go with that next topic, which is important, Bohr's atomic number. Okay, so right now this was all about by my side and all about the lecture. Now, if you have any doubt or query, please ask me. Sir, can you please allow the student to unmute themselves?